Hi, everyone. My name is Alex Goslen, and I'm a third-year PhD student at North Carolina State University. Today, I will be talking about robust player plan recognition in open-world games with multitask, multi-label learning. Player plan recognition is the task of predicting players' high-level goals and planned actions based on low-level actions that they take in the game environment. Plan recognition has the ability to enable player modeling, adapting task difficulty, and providing assistance to each individual player as they interact with the game environment. In this work, we try to answer the question of how can we improve computational models to predict players' goals and action sequences in open world environments. To do this, we construct a player plan recognition framework that utilizes players' in-game actions and their planning activities to predict two tasks, the player's goals and their plan for achieving that goal. To do that, we utilize an open world educational game called Crystal Island. It's a science mystery narrative that prompts players to investigate a mysterious illness that has spread across a remote island. Players can talk with characters, read books, and run tests in a virtual laboratory. To win the game, they have to identify the illness and recommend a treatment prevention plan for that illness. In this version of the game, we also incorporate a planning tool, which players can access at any point in the game. And as you can see here on the left side, they can select a goal or an action. And there are 20 goals to choose from. So if they find a goal that they want, they can drag and drop it into the center black box. There are 55 actions for them to choose, and they can do the same thing and drag it and place it inside of the goal clamp. Students can select as many actions as they want to place inside of this goal clamp, and they can also create as many plans as they want. And this is what we would consider a plan to be. So a goal clamp with several actions inside of it. Once they're done with that plan, or they don't want to see it anymore, they can drag and drop it to the trash icon on the bottom right, and they'll be prompted to answer if they felt like they accomplished that goal. Using these planning activities, we construct a framework around the intuition that players execute their in-game actions pertaining to their goals directly after planning. So what you can see here is a typical sequence from our game trace log. So players create plan 1 and 2, and then they execute the in-game action sequence 1 through 6, and then they plan again and create plan 3. Our framework would take this in-game action sequences input and plans 1 and 2 as the labels for that input based on our intuition. Similarly, any sort of action sequence occurring after plan 3 would get the label of plan 3. And here you can see is an overview of our framework. In this work, we incorporate an automatic plan completion detector because not all plans were marked as being completed in the game. And the way that this works is we check the game trace logs to see if plans have been enacted, and if they have, we remove it from the label set to reduce noise. We compare the goal prediction and action sequence performance using single task and multitask model architectures using LSTMs, and we evaluate both of these tasks with macro F measure. As we can see in our results for goal recognition, there was not a performance improvement between single task and multitask architectures. However, in our enhanced version that incorporates the automatic plan completion detection, we saw a major improvement, which indicates that that pre-processing step reduces noise in our data set. In our action sequence recognition results, we do see an improvement between single task and multitask architectures, and this could be because of the inherent relationship between goals and action sequences. So action sequences are driven by the goals that they are related to, which could be the reason for this performance increase. We also see an increase in performance with the automatic plan completion detection, which further shows that this reduced noise in the data set. In conclusion, we find that multi-label, multitask learning with automated detection of plan completion shows the most promise for predicting players' plans in open world environments. In future work, we hope to be able to predict goal abandonment with these plan recognition models, and we also want to implement these models in real time to drive player adaptive games. Thank you for your time.